question A on page 8 is your next question for gas stoichiometry. So at the bottom of the screen, I have the same details that you had on your page when you looked at the part 1 of this video, which was for question B. So I have the ideal gas law written out for you, your Celsius to Kelvin conversion, your review of molar mass, and your review of mole ratio. Remember, for mole ratio, you need to have a balanced equation, and that's where you're going to get your coefficients from the balanced equation to create some sort of conversion factor where you can move from one reactant to another, or from one reactant to another product, or even between two products. Molar mass, in this case for today, again, I'm giving you the molar mass, but just remember this is something that's going to help you go from grams to moles or moles to grams. So today's focus is really understanding what is STP when you're using it in a gas stoichiometry question. So STP automatically sets these conditions. It automatically means that you have a temperature of 0 degrees Celsius, which of course you know then is 273 Kelvin, and it means that it's at 1.00 atm pressure. So STP stands for standard temperature and pressure. Anytime that you see these words in a problem, that immediately tells you your temperature is 0 degrees Celsius and your pressure is 1.00 atm. There's a conversion factor that's reserved for just STP, and that conversion factor is that 22.4 liters of anything will always equal 1 mole of that atom, molecule, or compound. So if in a question you're told, or in a balanced equation, you know that you have 1 mole of oxygen, that automatically means that you have 22.4 liters of oxygen. And I'm just using oxygen as a specific example. You just want to understand that 1 mole of anything will always equal 22.4 liters, but only when STP is stated in the problem. So let's look at question A. Question A says when calcium carbonate is heated strongly, so there's calcium carbonate, I just highlighted it in yellow, carbon dioxide gas is released. So the decomposition of calcium carbonate helps us create carbon dioxide gas. The question now wants to know what volume of carbon dioxide gas. So that means that I'm going to be looking for liters. I'm going to go ahead and just write volume there in parentheses. I know it's liters because remember, I'm going to end up using ideal gas law. And so that means that I have to use whatever values were in R. So what volume of carbon dioxide gas measured at STP? So automatically I know my temperature is 0 degrees Celsius, my pressure is 1.00 atm, and I have the opportunity to use a conversion factor if necessary, which is that 1 mole of anything will equal 22.4 liters of that thing. I'm going to go ahead and write out my other possible form of the conversion factor just as a reminder. So what volume of carbon dioxide gas measured at STP is produced if I have 15.2 grams of calcium carbonate heated. So that means that I took 15.2 grams of calcium carbonate, I heated it up so it decomposed, and I produced carbon dioxide gas. Now I want to know what volume of carbon dioxide gas did I produce. I went ahead and told you it was going to be in liters. If you don't recognize that immediately looking at the question, that's okay. I'm going to show you how that works out today through this next series of steps. So normally I would tell you take PV equals nRT and let's go ahead and solve for V. But today I'm going to show you how to do this once you see the words STP given in the problem. So my only piece of data is the fact that I have 15.2 grams of calcium carbonate. It's written for me right here in the problem, and when I went to my balanced equation, I labeled it right there. That is my only data. I'm starting with 15.2 grams of calcium carbonate, and I'm trying to figure out volume of CO2. So all I can do is start with my data. Let me show you how you can complete this in one string equation. So I have 15.2 grams of calcium carbonate. I know that I want to get out of grams of calcium carbonate, and I want to eventually get to volume of CO2. CO2 and calcium carbonate are not the same thing. And notice that I'm going to have to move around in my balanced equation. I'm going to have to go from calcium carbonate to CO2. So I'm going to have to use mole ratio, but not yet. I first need to get out of grams. The only thing that's going to help me to get out of grams is molar mass. So I have the molar mass written out for you at the right side of the page, and it's boxed in red, and it's 100.1 grams per mole calcium carbonate. So I'm going to set it up so I have grams of calcium carbonate in my denominator, and then I want 1 mole of calcium carbonate in my numerator. And then I'm just going to fill in the 100.1 that I had already calculated. So now hopefully you can tell grams of calcium carbonate cancel, and you're left with moles of calcium carbonate. If you recognize this next step, I now just used molar mass. I can now get out of moles of calcium carbonate and into moles of carbon dioxide. So hopefully you now recognize that I needed to use mole ratio right here. So I'm going to set this up to say moles of calcium carbonate in the denominator so that those units cancel. And I want to be left with moles of CO2 in my numerator. When I go to my equation, this equation was already balanced. And remember, anytime you don't see any coefficients, because the 1 is always invisible, that's going to also be a sign for you that it was balanced. You can go ahead and double check and count all the atoms, but you have equal amounts of everything as reactants and products. So it's just a 1-to-1 mole ratio. Now when I go back to look at my units, my moles of calcium carbonate canceled out. And I'm now left with moles of CO2. Normally what we would do is that this entire portion that you just solved for, this would have been your N value that you would have plugged in for ideal gas law. But for today, the work is going to be a lot easier. All you're going to need to do right now is figure out how to get out of moles and into liters. And this is now where STP comes in and is really helpful. STP has the conditions that every 22.4 liters of anything will always equal 1 mole, or 1 mole will always equal 22.4 liters. And we were told that this is at STP conditions. So I can now say that 1 mole of carbon dioxide will be equal to 22.4 liters of carbon dioxide. If I go back to my conversions in my string equation, mole of carbon dioxide and mole of carbon dioxide cancel, and I'm left with liters of carbon dioxide. And that was what the problem was wanting me to solve for. So now, once you plug all this into your calculator, and what I would encourage you to do here is just take the shortcut. So you're just going to say 15.2 divided by 100.1. You don't really need to say times 1 or divided by 1 because it's not going to affect anything, but you do need to finish off by saying times 22.4. So hopefully your calculator stares back at you with the same calculation answer that mine has, and mine says 3.401 398601. Let's now determine significant figures. You only had one piece of data in this question, and that piece of data had 3 sig figs. That came from the 15.2. Do not use your conversion factor as data. Do not use 0 degrees Celsius as data, and don't use 1.00 ATM as data. That's just the set of knowns for STP. Only use the data given to you in the problem, which in this case was 15.2 grams. So all I'm going to ask of you for today is to give me this final answer in 3 sig figs. Don't forget the unit, and make sure that you circle or box your final answer.